Hi, this is Safi and this is my video for screencast of exam 2. Essentially, question 1, we need to sketch the reactor temperature versus feed temperature and irreversible exothermic reaction happening in CSTR. So here we have our bifurcation diagram. We can see from points A to C, the temperature is increasing and it's being heated up, but from point C to I is the ignition points, and then from points I to F it's essentially being cooled down, and then from points F to C is being cooled down way more. It's the extinguishing point, and we essentially know that in an exothermic reaction, as conversion goes up, the temperature increases, so the T initial increases with conversion, and then this adds energy to the reactor. This energy that is generated maintains the system's operation at the higher conversions, so then the initial temperature decreases and the conversion decreases until the extinction is essentially reached. And then here in question 2, we need to consider an reversible exothermic reaction taking place in PFR with a feed product heat exchanger used to heat the feed and cool the product. So to explain this plot, we have at point 1, this is the inlet to the heat exchanger. This is a cold fluid coming in as Tn. And parallel to that, we have the product stream of the heat exchanger, which actually starts at this position, L, which is the length of the heat exchanger. And it starts out hot at its entrance and it cools down to T out, and then T1 can actually transition to the reactor feed. And this is an exothermic reaction, so it can start at the bottom, but then the temperature increases as it goes through. And as we go with position across the reaction, conversion will increase, so temperature will increase. And temperature conversion are linearly related in some cases, which we are assuming right now. So, moving on to question 3, part C, explain physical basis why CA selectivity with C with respect to A is negative. Could this happen if second reaction were this instead of that? So essentially, the selectivity C with respect to A is negative when A is reacting away with B to form D instead of forming C. So essentially, in the second reaction, when A is being consumed to form D, then there would be no A to form C, and that is when the selectivity of C with respect to A would be negative. This cannot happen in the second reaction because in the second reaction, A is not being consumed to form D, so there's always a possibility for A to form B and C. But if the reaction where A plus B is becoming D, then there's a possibility that all of A will react to form D and C will not form at all, and that's when selectivity will be negative. Part D, in which reaction 1 and 2 is pressure drop significant? The pressure drop is significant in reactor 2, and this is because looking at the reaction, we can see that this is an expanding reaction, and we know that in an expanding reaction, a pressure drop will cause the reaction to favor the formation of the products. And in reactor 2, the selectivity is higher selectivity of C with respect to A is higher than in reactor 1. So the formation of the product C is being favored since the selectivity is higher. Question E, in which reactor 1 or 2 over yield be higher? The same thing, in reactor 2 the yield is higher. And how do we know this? Because we know that the yield is the moles of C formed over moles of A fed. Which I previously stated, and the pressure drop caused the equilibrium to shift towards the side reaction where there are more moles, and that is the side of the products. Looking at the graph of reaction 2, we see that the selectivity is higher than it was in reaction 1. And we know the selectivity relationship between selectivity and yield. So as selectivity increases, yield is increasing, and since the selectivity is higher in reaction 2, the yield is higher in reaction 2. So this is question 4a. Without doing calculation, would you expect the Nernst molecular diffusion coefficient to be larger? Explain. I would expect the molecular diffusion to be larger because, as stated in the problem, it is highly dispersed. This is highly dispersed, which means there is a larger surface area. If there is a larger surface area, that means that the molecules are more likely to bump into each other more than they will bump into the walls. And if they are more likely to bump into each other than they're likely to bump into the walls, then molecular diffusion is larger. But we know that the Knudsen diffusion dominates since the mean free path is bigger than the pore radius. And you can see this in the equation B below, where you can see that it's obviously dominating in this transition equation. So, moving on to question number 5, part B. Are the molar flow rates in the numerator expression of the inlet or the local flow rates? So they are of the local flow rates, and we know this because it is a PFR, and we know that in a PFR, the conversion changes with length. Or the concentration changes with length, or the conversion increases as you go down the PFR. So the heat capacity values are not constant, and this will make the flow rates local. Part C in polymath, for a conversion of 90%, I got a U over D value of 6,460, and the reactor maximum temperature was 346.7, which is essentially 347, and the conversion that I got was X is equal to 0.9006, which was the lowest conversion I could get, and this is my U over D value. And to answer this question, how does U over D affect conversion? In U over D, the diameter is essentially decreasing as it is in the denominator, and it's being divided over by a large number. And when you are decreasing the diameter, you will need to increase the length in order to keep the same volume, right? And we know that increases the length increases the conversion in the PFR. Increasing the length means there's more time for the reaction to take place, and there will be a better conversion, essentially.